Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 12.1.3, which is combinations. We'll be finishing off our adventure through the counting principle and all these different ways we can formulate something. In 12-28, it talks about 5 members of the Spirit Club have volunteered to be on the club's governing board. These members are Al, Barbara, Carl, Dale, and Ernie. The club members will select 3 of the 5 as board members for the next school year. One way to do this is to select a president, a vice president, and a secretary. Another way is to elect a governing committee of 3 where all members would have the same title. So right now it looks like they're setting us up for a situation where order is going to matter, and then a situation where order is not going to matter. So it says, how many different lineups of officers is possible? That means president, vice president, and secretary are chosen. So thus, Al as president, Barbara as vice president, and Carl as secretary would be different than as Al as president, Carl as vice president, and Barbara as secretary. Okay, so from here, we got 3 different outcomes here. Of the 3, it looks like I could choose 5 of them, to any one of the 5 to become president. That means 4 remaining and then 3 here, which would essentially be 5 factorial, except I'm about to lop off the other 2 factorial, right? These guys are gone. So we've done this in the last section here, where that's going to be 5 minus 3 factorial. We saw this as 5 permutation 3, which would then give us 60 options. Oops, can't spell. Options. Okay. Part B says how many different 3-member committees are possible. In this case, it might be a good idea to make the list of all the possibilities. These are called combinations. So I'll go and type these out. That way we can have them in good handwriting. So the first one is Al, Barbara, and Carl. Then Al, Barbara, and Dale. Then Al, Barbara, and Ernie. Let's go and move this down here. And then I'll go and do another list of Al, Carl, and Dale. Al, Carl, and Ernie. Al, Dale, and Ernie. I think I'll move that down. Sorry, the white on the white background doesn't really help out. Here's another one. Barbara could have led the team with Carl and Dale, Barbara, Carl, Ernie, then Barbara, Dale, and Ernie. In which case, Al, he's gone. Yeah, we don't really need him in this scenario here. And then the last one is Carl, Dale, and Ernie. So these are all the possibilities that you should have come up with here. Now, notice how in the committee, if all of their responsibilities are the same and they have the same title, the order isn't going to matter. So I don't need to consider Carl, then Al, and then Barbara, because that's the same situation as Al, Barbara, and Carl, or if Barbara led the team first, right? So these are all the possible scenarios for a combination. So it looks like there's only 10 options here. So now it says Felicia has also decided to volunteer for the governing board. How many different officer lineups are available now? Well, in this case, now there's 6 people in the running, right? So that would be 6 and then 5, and then 4, right? And then the 3 factorial gets lopped off, right? So I got 6 factorial over 3 factorial, or in other words, I could say 6 factorial over 6 minus 3 factorial. In other words, 6 permutation 3, and that would be 120 options here. Again, this is back in the officers situation, if we're going to do officers. And then, if I wanted to make a list of all the different possibilities, I'll go and pause real quick because that's going to take a little while. I'll pause and then I'll come back with it. Give me a second. So after doing all the combinations here, it looks like there's a total of 20 options. And that's if they all decide to hold the same title. Now in part, well, I think I misread that. I think this is part C, part 2. So sorry about that. Let me just fix this. C, part 2. In part D, it says, since there are more volunteers, the Spirit Club has decided to appoint another committee member. If a treasurer is added to the list of officers, how many different ways are there to select 4 officers, and then committees? So we've got to do it with a 4-person scenario now. So D, I'll go and fast forward this one. This one is going to be, looks like, how many people do we have chosen here? It looks like there's going to be 6 people with 4 different assignments. So 6 permutation 4, right? So that's going to be 6 factorial over 6 minus 4 factorial, which is going to be 360 options. And what they're trying to get you to do right here is they're trying to get you to see a pattern that we're going to establish in the next problem. And then if we look at the number of the number of committees, that will be, let me go and type this out here. I'll pause real quick and then type it out. All right, looks like we're dealing with 15 options here. I was debating on whether or not I should type that out or not, but no worries, I totally typed it out. Okay, so this is what we're looking at here. It looks like when order matters, there's more options than when order doesn't matter each time, right? 60 options versus 10, 120 versus 20, 360 versus 15. We're going to try and establish a pattern about that in the next problem. I'll be right back with it. In 12-29, it says to compare your results that you got from 12-28 when you had a permutation versus a combination. How do the numbers of permutations and the number of combinations compare in each situation? So let's take a look at situation 1. With the permutation, we had 60 options. With the combination, we had 10 options. So it looks like there was, so it looks like 6 times C equaled P, right? So in other words, 6 times the combination gave me the permutation. In situation B, we had 120. For the permutation, we had 120, and the combination, we had 20. So if I was to divide them out, that would be, looks like 6 again, right? So 120 over 20 would be 6, right? So it looks like there were 6 times as many permutations as combinations. So I'll go and type that out. So 6 times, there are 6 times as many permutations as combinations. And then in the last situation, that way we're not confused here. In the next situation, the permutation was 360 and the combination was 15. So if I do that means if I do 360 divided by 15, I get 24. So in this case, there are 24 times more. So 24 times as many permutations as combinations. So what's the relationship that we're going to try to extrapolate here? Well, if we look at each situation, right? If we look at each situation, in the first situation, we had 5 permutation 3, right? We had 5 permutation 3. The next one we had looks like 6 permutation 3. So 6 permutation 3. Then in the next one, looks like we had 6 permutation 4. And so that is how we got these numbers. But how are we able to lessen the number when we do the permutation and when we do the combination? Well, if by multiplying by a number gets me a permutation, that means that then dividing by that number will get me a combination, right? So if I divided this thing by 6, that would get me the proper combination that I was looking for. In other words, that got me 10. If I divided this thing by 6, that got me the combination I was looking for. When I divided this thing by 24, that got me the combination I was looking for. The thing about 6 and 24 that the book is asking you to make the connection with is that 6 is really 3 factorial. 3 factorial. And 24 is really 4 factorial. So what they're asking you to make the connection of in part B is that a combination, right? A combination is equal to the permutation divided by r factorial. And that's going to get you something known as NCR, which in this case, if the permutation is going to be n factorial over n minus r factorial, you divide that once again by r factorial. But dividing by r factorial is the same thing as multiplying by 1 over r factorial. So the most simplified version of this formula is n factorial over n minus r factorial times r factorial. And that is your combination formula. And I think we accidentally just did D on accident. Sorry about that. So this is D. I'll cycle back and take care of C. It says test your conjecture by calculating the number of permutations and combinations from 2 items chosen from 6. Does it work? So we got 2 items chosen from 6. So we've got 6 is going to be our n, and our chosen is going to be 2. Oops, 2 is going to be r. Sorry about that. And so if I do 6 permutation 2, if I do that in the calculator, right? So 6, I'll go and just do this in the calculator real quick. Permutation 2. That's going to get me 30. If I divide that by 2 factorial, right? If I take 30 and divide it by 2 factorial, I get 15. So if I decide to do 6 combination 2, that would be 6 factorial over 6 minus 2 factorial times 2 factorial. What would that get me? That's 6 factorial over 4 factorial, 2 factorial. And if I was to expand this and do this actually mathematically without a calculator, I would get 6 times 5 times 4 times 3 times 2 times 1 over 4 factorial is 4 times 3 times 2 times 1, 2 factorial is 2 times 1. The 4 factorials cancel each other out, and I get 30 over 2, getting me 15. So this combination formula is where things are at. So the bottom line with this lesson is that a combination is like permutation, except order does not matter. So it counts the number of different ways a scenario can outcome when order does not matter. And I think that will take care of combinations for us. As always, please leave questions or comments in the comments area. And congratulations, this is the last episode of Integrated Math 2. So congratulations on finishing. I will see you in the next class.